something at a relaxed pace. All right, we are ready to go. Um, there's not, to be fair, this is antibiotics. There's there was not a great deal of specificity. I guess that would be the word. So I'm going to review it sort of the way they have it here, and in the this particular PowerPoint from this textbook, from the Cowan textbook. Even though they're both textbooks from McGraw-Hill, the other textbook, the Nestor textbook that I like very much, has a much more thorough description, which I have used utilizing for basically 25 years. That really gives pre-health oriented students a tremendous advantage because I can give you a lot of the history historically about these things and what we use today and how we use them. So, I mean, I kind of tend to do it this way, but I want to make sure I cover everything here as the basics and then adapt. So I'm trying to mesh the two of them together. So and this is where you might remember looking at this slide, trying to find the quote unquote perfect antibiotic, if you will, or the perfect agent to use for bacterial infections. And this is all vis-a-vis bacteria, though there are some of these that work on both, to be fair. We'll go over that in a bit. And you can see the two major areas are attacking protein synthesis somewhere in the ribosome, some way, shape, or form. So I just classify those as their means of action is to somehow interrupt protein synthesis. By and large, they are not bactericidal. There are some exceptions. That's important to note coming up that are there. Cell wall is the other giant category. That's where penicillins and cephalosporins, those are the big players that are there. They are effectively all bactericidal. Why don't we use them constantly? They have their limitations, not the least one of which is allergies that are there. The fact that a membrane is a membrane is a membrane for the most part. That even though we are seeing increased usage of these, the side effects are massive. And these are starting to become drugs of last resort for what are the development of these superbugs that we'll talk about. And they really don't give it a lot of shift into this particular, into the Cowan textbook that we use here. But, decisions on that are above my pay grade. Okay. So, and we have to spend a certain amount of time talking about quinolones and rifampin because these are used tremendously. They're really the long arm of treating gram-negative infections. I can't tell you how many times I prescribed them over the years, how valuable they are, how much we use them today. And at least a little commentary on tuberculosis drugs, of which rifampin is one of the major ones. And you might recall me mentioning this particular player we call combination sulfas that inhibit a pathway called folic acid. I'm reviewing this because if you're like me, when I was in school after spring break, we forget everything possible. And I am delighted to see you here, Brooke, rather than incarcerated. I heard what was going on in Fort Lauderdale. I figured you were. Yeah, pardon? Yeah, I understand that.
Yeah.
At least you got some sun. Thank goodness you weren't on a police blotter. I was looking. Oh, there was all sorts of stuff, some crazy stuff going on in some of these places. If you had gone, you'd have been there too. Yeah, she's not talking. Thank goodness. Oh, stop. It's not that funny. I had to get a shot in. Look, I spend it quietly with grandchildren. You happy? So these combination sulfas have been around for a very, very long time, and because they were to some extent have fallen out of favor, because they're also interestingly not really antibiotics in the classic definition sense, but because they hadn't been used, all of a sudden we found that they worked well on what we'll talk about that isn't really in this chapter from the Cowan textbook, community-acquired MRSA. And so these are just the different categories. And the other PowerPoint, I'll go over the differences. They comment a little bit, and they have at least a little bit of the chemistry. Not that I want you to memorize chemical structures, not at all, but to understand what the differences are between penicillins, I beg your pardon, G and V, ampicillin and amoxicillin, okay, nafcillin and cloxacillin, and the role that clavulanic acid plays, although I would have put an O in there rather than an A, but the spelling is not important. That's a really important agent, because you have to understand kind of how penicillin evolved, and a little bit of what I'll be presenting to you, if not today, on Wednesday, will be this. We'll probably take the whole week on antibiotics on this particular chapter, I would think. And then after that, probably the following week will about kind of be how diseases spread, which is been a little bit of epidemiology. And after that, we'll look at specific systems for the last 4+ weeks of the term. Then home stretch. Happy. So the cephalosporins, which are in the same category as the penicillins, the cell wall agents, extraordinarily important. Again, more than half of all prescriptions for antibiotics are in this category. If you can't possibly know enough, and you have to understand why. Okay, they're in that category, and how they, even though they're similar, how they're different, but how they're similar to penicillins. These are important historically and still used. A lot of times you run out of things, but inevitably, a lot of these were older drugs that probably have fallen out of favor because we found things that are more efficient, but they're of some note historically. And then the whole miscellaneous thing that's here again, bacitracin is topical. This is an anti-tuberculosis drug. Vanco, very important because it was, and you're going to see it. This is one of those agents that is on the pecking order. And I'll give you my pecking order for how we treat MRSA down the road. And Vanco is sort of really at the very end of it. Most because we used it so much, because it's very, very, very effective against gram positives and horrible. Doesn't work at all against gram negatives. You can't get through the membrane. Okay. The difficulty is when you start using your last resort drug early, before you tried everything else, and resistance began to develop. Therein was a big problem. So we'll go into like bits about those. Protein synthesis, the aminoglycosides are somewhat limited. As you will see, this is streptomycin, sort of the parent. They target, it doesn't matter whether it's 30S or 50S, but the problem is they have a certain amount of toxicity, so we still use them, and this is the category where we're able to attack a very nasty bug called Pseudomonas aeruginosa, something you work with in the laboratory. So it's very, very common. That doesn't make it less problematic. It's something that's on, by and large, that's part of our environment now. It's on your skin, it's in the soil, it's a soil bacteria. So, I mean, if you're looking for something that shouldn't necessarily be on the skin, but is, because it's hard to avoid getting in contact with dirt. I mean, think of it. You slipped on your shoes, maybe you tied your shoes. Next thing you know, there's soil on there. Now you picked up something, got it in your hand. Doesn't take much. So we'll talk about that. Tetracycline is important historically. Some changes they've made. Certainly, again, this is the drug of choice, an important term. Because when it comes in clinical, can't be unaware of the legal implications. What drug of choice means is that's the drug you're supposed to use. Drug of choice, and I commented on this earlier, addictive disease is the drug of choice. If you're doing rehab nursing or rehab intervention, when someone's a drug addict, we ask for their drug of choice, like cocaine, heroin, speed, whatever. Doesn't matter. But the term drug of choice from a medical legal concept is that's the agent or family of agents you are supposed to use for this particular condition, which means you better have a darn good reason if you didn't. You have to be aware of the side effects and all that good stuff. And there's an important, Clindo is an important role, clindamycin. These are relatively new categories, and these are really categories that have been developed because of an attempt to fight MRSA. That's where a lot of these new categories have come from. And this one, interesting, even though most of these, the streptomycin category, they're bactericidal, all the rest of these are bacteriostatic. I mean, and what you're hearing every time I say that is underscores the importance of why bactericidal is better. Static leads, it's always something a physician would not choose given their, and it's one of those sort of things we look at. Again, when you look this week at those Kirby Bauer plates, the big zone doesn't matter. That's just a number. Again, if it's bacteria static and another one's bactericidal, and both the zones are categorized as susceptible, you pick the bactericidal as long as there's not a good reason not to. Period. It's not a debate. Oh, there's a giant zone. Nobody cares. That's again because it is not a quantitative test. It is a qualitative test. Yes, no, maybe, bless you. Sit outside. Just right. I've already had it with little kids coughing and sneezing on me. And they have an annoying tendency to cuddle. It's like, and want to be read to in bed. And inevitably, when I, as a grandparent, go to one of these, my son regales them of all the trouble he got into and how I inappropriately reacted to it. He tells the same effing stories all the time. You know what Dad did? Well, everybody gets a good laugh out of that. And so we'll look at, these are the combination sulfa drugs. We'll take a look at those. We'll take a look at these, the fluoroquinolones. I'm just giving you sort of going over. You can see they relatively generically, they do make a comment in this PowerPoint sequence about how we tend to be using these a bit more. And they're accurate about this, that we're going to encounter something that's cool, and I'll just give you the term. You don't have to write it down or anything, so I'm probably not going to ask you questions about it. They're called ESBLs, extended spectrum beta lactamase inhibiting bacteria. They're kind of in the category of, I know, so it's a long name. Thank you. You can only hope. So, don't worry about that. Broad spectrum versus narrow spectrum today. Again, the modern definition, for instance, broad, and again, broad doesn't mean better. Tetracycline works on gram positives and gram negatives. Not particularly great. Selectively, yes. Useful agent. Polymixing principally is more often used on gram negatives. That's the difference between those. And you see a lot of the alterations we made in penicillins, these chemical substitutions, which we call semi-synthetic penicillins, were done for the reason to alter their spectrum of activity, to extend it, to enhance it, to make it more useful for certain kinds of conditions. And then a nice little chart and things that we use, I mean, it's like, and it's not bad. We know that there are certain kinds of mycobacteria that we find to be normal. A ton of gram negatives are normally part of us, a ton of gram positives, even some chlamydias, believe it or not. Rickettsia, they spelled that wrong. They didn't put the spell check on. It was named after a doctor named Ricketts. And we touched on it ever so briefly, particularly not so much here. It's kind of a teeny tiny gram negative that lives inside cells, and it's important for one of my favorite disease names, Rocky Mountain Spotted Fever, which, believe it or not, is more common here in Pennsylvania than in Colorado. It happens to be borne by ticks. So and you'll hear me say it again and again. Follow the vector, you'll figure out about the disease. Control the vector, control the disease. So they're going to show you this chart in the other PowerPoint sequence. So I'll give you a little quick introduction to this chart. So this is this interesting structure here called the beta-lactam ring. That's the special sauce that works, why penicillin drugs work on bacteria, particularly gram positives, because that chemical structure gets in the way of peptidoglycan from forming and making a cell wall. Period. That's the beauty of it. Without the cell wall, bacteria rely on that cell wall to hold everything inside intact. If the cell wall isn't there, effectively, the bacteria explode. Remember, it's a cell envelope, not like a cell wall per se, but this is a wall and this is a layer of protection. This is a membrane. This is another layer of protection. They're intertwined. They're married. If you destroy one part of it, you destroy the other. That's what happens. And this beta-lactam ring is the key. Cephalosporins have the same ring. So collectively we call them beta-lactam drugs. So this is the original player. And the only thing that they tinkered with, and then rather than losing numbers, what they found is naturally occurring were two types of penicillin. One was here, one was here, and they named them G and V. Interestingly, V, and this is a very consistent finding, was relatively penicillin G, which was the first one. Okay, very low cost, been around forever. Okay, big problem with it, it doesn't work very well orally. And people would much rather be able to take, pills on a regular basis and have to go in and get shots or an IV all the time. Very inconvenient to do at home. Those are a lot easier to do outpatient. But penicillin B, actually, so you're going to see this comparison exist a couple of times a year. Penicillin G better by injection, penicillin B, or we'll get to all this other penicillin A's and things like that. That's kind of a defense mechanism. That since the beta-lactam ring is the key, okay, Staphylococcus, a living thing, what they started to do is they were being bombarded by penicillins. Remember, originally 90 to 95% of all Staphylococcus aureus, certainly Staphylococcus epidermidis on all over the skin all the time, they were all very, very readily susceptible. And they were destroyed by penicillin. But the penicillins who survived that onslaught, that chemical warfare, developed a mechanism. They secreted an enzyme. The enzyme had this name, it's called penicillinase. The ASE means, remember that means enzyme? Okay, so when you hear every time you see the suffix ASE, it's an enzyme. And what did it do? It destroyed the beta-lactam ring. So the first thing that happened with penicillins is these guys didn't work. So we have to initially, after, I would say probably as early into the late, so penicillin came out and was used exclusively from roughly 1941 on, and it was really the principal agent being used for a lot of infections because not only because it was oral, but because of the availability of it, the relatively low cost of it. And we began to make some discoveries of other antibiotics like the streptomycins, which have a lot of toxicities, tetracyclines, which weren't particularly good on staphylococcal and streptococcal infections. And it didn't take long for them to see we were going to have to make some changes. And eventually, when I started, so by the time I started to hear about these things, maybe 20, 25 years later, started to hear about particular penicillins that, so if we had a penicillinase, these were agents, penicillins, that were effective against penicillinase producing staphylococcus. That's where you start to see this next category. Those agents that were made in the lab, semi-synthetic, were nafcillin, and again, and also one called methicillin, very famous because we even defined MRSA. But they had methicillin and nafcillin, but they had the same problem. They were active orally. You could use them for injection, so they made an orally active form. The orally active form, oxacillin. So not like we learned. Every time somebody came in with a resistant Staphylococcus aureus infection, what did they do? They gave them methicillin or nafcillin intravenously or intramuscularly by injection, but they gave them oxacillin. And they tinkered with it. They had floxacillin and dicloxacillin. There's all sorts of members of the family. Lots of them. It'll work the same way. Different manufacturers formulate them slightly differently, gave it different. And you'll see that a lot in pharmaceuticals. Now, pharmaceutical companies kind of go against one another. So that's really, you're looking at down here. Okay, so not usually susceptible to penicillinase, so it could resist that. This had poor absorption, resistance, and now you rarely use it because they made the bacteria fought it again. They dealt with this sort of unique chemical substitution over there and attacked that. Bacteria are pretty smart. And so now we really had a problem. And this was the development of what you and I universally refer to as methicillin resistant Staphylococcus aureus, or MRSA. This way. Just to let you know. So the question is, what do we use now? And then you'll start to see where the pecking order came from. We're not done yet with this stuff. Penicillin was so good. The big problem with penicillin is great on peptidoglycan. Trouble with peptidoglycan is on the outside, and gram-positives, great. Very good for gram-positives. Not so good for gram-negatives unless they're really easy to kill. So what they did was they began to tinker with this. And now you're down here to what's called ampicillin and amoxicillin. Names that you heard before. What they did was for ampicillin, they ran into the same problem. They wanted to broaden the spectrum. So broadening the spectrum, remember, we're narrow and broad spectrum. Broad spectrum, I'll just use PCN for penicillin. The first one was ampicillin. They actually added some type of amino group, one of those NH2 type of groups in some chemical way. It was ampicillin, and that didn't work particularly well orally. Same problem. So they changed it and tinkered with it, and voila, they had orally active. It's very famous amoxicillin. Anybody here who's had ear infection and weren't allergic to penicillin, guess what? You got amoxicillin. And why it's so relevant to this class? This was developed here, research done here at Heidinger Hospital. Yes. All I did is use worldwide the strawberry liquid, little pink chewies. Kids were very happy at that. We were in good shape. You know, one kid gets an ear infection, your arm is never can tell. So amoxicillin versus ampicillin versus amoxicillin. And when that didn't work, and that was all about being able to cross that membrane and get in, to get through that outer membrane, so it'll work on the peptidoglycan. And they found out that even to really make it broader, and their particular attention to this guy called Pseudomonas, because it was becoming such a pain to treat, they decided to extend the spectrum. So the next step, when you see something called extended spectrum, and so on. They were designed for really harder to treat gram negatives. Really, Pseudomonas would really have been through. The trouble with why we don't use them that much, they're not particularly easy to tolerate. Okay? They were a better choice because aminoglycosides, as we'll get into, are toxic. They have lots of interesting names. We even probably have some tablets in the lab. Kirby Bauer from Icaricillin. So it's not just very broad, the appropriate term is extended spectrum. And now we get back to how did the bacteria respond to all of these? We're bombarding them with a series of agents, all of which rely on penicillin and rely on this beta-lactam ring. Well, staphylococcal organisms, by and large, produce one called penicillinase, but that's not the only one. There's another one that's produced by things like streptococcus, another enzyme that's produced by gram-negatives that works very similarly. It's all about targeting that beta-lactam ring, and so we give it the name beta-lactamase. Even some staphylococcal organisms make it. So beta-lactamase is mostly the defense for non-staphylococcal organisms, but also some staph aureus. So penicillinase and beta-lactamase are similar in the fact that they attack that very famous lactam ring, but they're limited. And frankly, the penicillinases are harder to find agents for than beta-lactamases. So let's think if we running around drawing a crazy person. So what happened? You had an ear infection, and usually the ear infections are being used to treat kind of easy to treat gram-negative, you'll hear about called Haemophilus influenza down there, and a kind of streptococcus called Streptococcus pneumoniae. We'll get to that when we talk about respiratory. A lot of times they make beta-lactamases. So how do we work the problem? Well, the amoxicillin being blocked by lactamase. They came up in the lab with something called a beta-lactamase inhibitor. It targeted the enzyme specifically. The theory was if I can block the ionation, IBOR, start. We came up with a beta-lactamase inhibitor, figuring if I put this together, it would block that, the amoxicillin stop. The name of that is called flavulonic acid. So you took amoxicillin, orally active, plus flavulonic acid. Basically, you were powering up the flavulonic acid. That's a very famous name commercially. Called it was augmenting, enhancing the activity of the amoxicillin. So a lot of times when we have by culture Kirby Bauer, and typically we test with Kirby Bauer both for penicillinase producers and beta-lactamase producers. There's a whole lot to that test that you did in lab, and you're going to look at the results this week. Voila. God, we have content this morning. You're all looking at me like, must we go back to this nonsense? Rather than, see, Brooke's excited. She's like, I'm so happy to be back. All right.
You know me.
Yeah, I know. You're good to go. I can see, I'm overwhelmed with the enthusiasm here in the class. Okay, nobody thinks you're funny. They never do. My wife doesn't believe it. I'll come back to all this. We'll revisit it again. I know that's a lot of material to digest. I know. Okay, different things. This is about the shift that they gave you with regard to, they didn't give you a whole lot of information in this chapter. Probably because you don't need it right now. But here's the response I've got from every single nursing school program that I have taught at, which includes CCAC BC3, Westmoreland County Community College, Shadyside School of Nursing, West Penn School of Nursing, including here, just to name a few off the top of my head. Boy, when they come out of your class, they really know a lot about antibiotics. That's why I'm doing this. Okay? It'll make that pharmacology that you're dreading go maybe just a little bit easier. So bacteria and biofilms differently. So we can't use things when we know biofilms are part of it. So they're often not affected by the same antimicrobials that work against them in the absence of the biofilm because they can't penetrate. So they express, when they say a different phenotype, they behave differently, different susceptibility profiles than ones that are not. So one of the things we look for in certain agents is the ability to penetrate the biofilm. You'll see that because you might remember me in passing saying Clindo, which is short for clindamycin, is very useful. It penetrates biofilms really well. Why don't we use it more? Horrible on your stomach. Horrible on gastrointestinal. Used a lot of it. So they do different things. There's a lot of different strategies. So here, that daptomycin, again, that attacks cell membranes. It's very harsh. Adding DNase is an enzyme that we use in the lab a lot of times to test certain bacteria. And I mean, adding that to antibiotics, I mean, it destroys DNA. Think about that. We don't want to get where it shouldn't get. Okay. And now this is done a lot, impregnating devices with antibiotics prior to insertion to prevent colonization. They do a lot of that with catheters, a lot of that with, particularly ones that are designed to be indwelling for long periods of time. Because when you remove it, in the old days when we had Foley catheters, I stayed in for 48 to 72 hours, which were common in the hospital. And you typically changed them out every 2 to 3 days. We have to culture the tip of the catheter. It was just covered in yuck. And really, the only thing that was passing around that theoretically should have been urine. Passing through it, eventually, why did the outside get so covered in yuck? Well, when they took out implants, orthopedic implants, they were covered in slime layers. Just yuck. For a while, we had to remove a lot of breast implants because they were used as silicone-based implant. And now they use, basically they're filling with saline now, inserting, basically a biological bag wherever they're doing the augmentation and filling it with X amount of saline, typically normal saline, just in case it bursts and we have problems. So there's all sorts of nuances with this, and there are some problems that even induce biofilm. So there's a lot to it. And then they go right to antifungals. What the heck? Okay, antifungals are a whole different problem. I'll go back and revisit the fungi. I wanted to go through this PowerPoint for you. Because understand, whether it's a fungus, whether it's a protozoan, whether it's a worm, all of those things have cells that are like our cells. So if we do something to damage their cells, it's going to impact our cells. They're just too similar. You have to look through something that's a subtle difference and hope that and there's going to be side effects. There always are. That's the big problem with taking care of things that are caused by other eukarya. Okay, and that's yeast and fungi. And I mean, fungal and yeast infections are extraordinarily common. Parasitic infections, typically like malaria, as you will see, Trichomonas vaginalis, giardiasis, amoebic dysentery, they're all from protozoan agents. They're a pain in the neck to treat. We have some good stuff to treat them with. So drugs that are, why can't we use antibiotics? They don't work. There's one antibiotic that actually works on some of these, and I will share the name with you. You're going to learn a lot about it. Similarities between fungal and human cells mean that drug toxic to fungi will harm human tissue. So there's really no antifungal agents that work effectively. The one I'm going to be talking about is called an antiprotozoan. Only a few agents with special antifungal properties have been developed. They've tried a lot of different things. They don't work very When I was learning about this in school and in my early days in residency, we're pushing 50 years, you were afraid to have to use those things other than topically. Because most of the time the side effects were worse than the disease. If someone had a deep fungal infection that got inside, say in their lungs, we gave them a chemical called, you have to write this down, called amphotericin B. It usually caused deafness. I mean, short of being a situation where they were going to die, it's a matter of this. And as you'll learn in your career, whether you're in a medical career or not, it's always about this. It's the balance of the scales, risk versus gain. What do you got to win? What do you got to lose? And that tenet that applies to medicine, applies to nursing, applies to anybody in the healthcare field. First, do no harm. Not easy to remember, but it's very, very critical. So this is where they were. So I saw about amphotericin B. Okay. All this type of stuff. And it could be used. Okay. Used to even treat kinds of meningitis. We'll talk about down the road respiratory histoplasmosis is something we'll talk about because it happens in and around this area, not with a great degree of frequency. But this stuff is horrible. Thankfully, these were other categories that are there. They came up next with this category called the azoles. The whole ball game, because they're eukaryotic cells, fungi have, what they have common with us is the cell membrane. Our cell membranes, all animal cell membranes, commenting about this, stabilize cholesterol. Fungal membranes are stabilized by ergosterol. Very similar to cholesterol, but not the same. The agents that work best for antifungals interfere with ergosterol. So they block the synthesis of ergosterol. You want to call it ergosterol? Go ahead. I don't even know. I may be accenting the wrong syllable. My son had a whole, this is the military, you'll get the same list. He had a whole list on his phone of stupid jokes he must use, and at least a half dozen of them I couldn't tell in this class and keep my job, but we digress. Oh, stupid things. I can't even remember them. I blocked them. This he had to point this out to his Saturday night we were playing cards. Played cards with there were 6 of us, my wife and I, my daughter-in-law and son, and the 2 little ones the little boy's going to be 5 next month, and the little girl will be 8 in June. We're playing Uno. They got that machine, that Uno action that shoots cards out at you. You know what I'm telling you about? Oh my God. You know who got bombarded first? My soon-to-be 5-year-old, because I just got Uno. He gave me one of those press twice cards. First one beep, the second one. I felt I was picked on. We had never played that with you. It's fun to play with the kids because it's easy, numbers and colors, and that works. Little did I know that this 5-year-old, who actually understands a bit about how the immune system works, one of those. I'm thinking of giving him the immune test we're going to use in A&P. Okay, we'll see how he scores against the average. Moving on. So this category I like very well. Okay, clotrimazole, topical. It's called Lotrimin. If you go into any pharmacy on non-prescription, anywhere where they have like foot creams and antifungal creams and all that type of stuff, both of these are right there. These ketoconazole and fluconazole, maybe my favorite. Okay, fluconazole, also known as diflucan. See, these used to treat infections, skin, mouth, vaginally, topically. These orally, you can treat both of these. It's called diflucam. I used to give it to diabetic patients whenever I gave them cephalosporins, because most of the time they were going to get a vaginal yeast infection. So a diabetic female patient, it was like, that was part of their history. I had a little Post-it note on my chart, with the color, or just said diflucam, and I knew if I was giving them a prescription for a strong antibiotic, they're getting diflucam. I never had a problem with it for all the years I used it. So really, this is something that really improved things, because the rest of these were awful unless you were dealing with, aspergillosis, potentially fatal. This is another one that the terbinafine, the allylamines are another category which active both topically and orally. Okay, so all of these ergosterol synthesis. This is how they work. They interfere with the sterol synthesis. That's their big way. The big way they work. And they're the ones that have been the most successful. As we move on, and we're going to revisit these again, anti-malarials. I was just looking this up because I was unfamiliar with this artemisinin, if I'm pronouncing it. This is, for years, quinine alkaloids. Quinine alkaloids come from a plant, okay, that thankfully happens to grow in tropical climes like rainforests. And we didn't really know about them. The natives knew about them very well, because malaria is carried by mosquitoes. And anytime you're in a rainforest or similar area, and historically, our Western medical science learned about that when they went to dig the Panama Canal at the very late, like 1880s, 1890s. And you're going through the middle of a rainforest from the Atlantic to the Pacific, a big project. Long time to dig those canals, basically, passageway between the two oceans. People were getting sick all the time with malaria. The natives there started giving them extracts that they made from those leaves. The scientists there, the doctors here, were like, what is this? And they found out they were quinine alkaloids, and they are very, very useful. And for years, we played around and tinkered with them. Again, I don't think they classify as an antibiotic because they came from a plant, not a microorganism, and they made quinolones. When there was a whole lot of controversy, which was probably inaccurate, about something called hydroxyquinolone during COVID. Oh my God, the government didn't want people using it. Oh my God, because it actually worked. But we digress. But these are chloroquine and primaquine were the mainstays. This is a little bit different. And I wonder if I still have it cooked up. Probably do. Up on here. No, I didn't. Here. Natural compound, again, from sweet wormwood, anti-malarial, both chloroquine and chloroquine resistance. They give you the formula that they're, and again, this damages its protein inhibiting an enzyme. It works by generating free radicals, which we've heard about a lot. So that's very interesting that now they have found, and again, that's it. You're constantly with diseases like that. I'll say it for the 100th time and another 100th time. The number one killer in sub-Saharan Equatorial Africa, malaria. Malaria. You go to one of those areas, that's what you worry about. That's why whenever you go to an area that has a lot of mosquitoes, you're sleeping with mosquito netting, taking preventative anti-malarials. That's all part of the drill. My micro class, we did that virtual vacation thing. If you're going to travel, do that. So again, I wanted to give you some background as to why I think this stuff is important. So, and this is a major player. This is the double duty drug. Most protozoans, malaria is not included, most protozoans work by anaerobic metabolism. There are very few antibiotics that take care of anaerobic agents. The most problematic strict anaerobe dies in the presence of oxygen is something, if you work in a hospital, you see every single day. Talked about it already. It's called C. diff, Clostridium difficile. Drug of choice, metronidazole. It's known as Flagyl. So either name works, Flagyl. It only works on organisms, be they bacteria or protozoans, that operate anaerobically. Interestingly enough, so when you hear about contaminated well water, that's amoebic dysentery or giardiasis, also the drug of choice. And as I said to you before, the second statistically most common, and the only one of these that's treatable, so it'll make it go away and not come back, assuming you don't recreate the environment for it, Trichomonas vaginalis. Statistically, the second most common by way of occurrence annually sexually transmitted disease. And the drug of choice, metronidazole. It'll give the person who gets it, male or female, whoever the person or whoever, however it is passed, if it's heterosexual or homosexual contact, okay, it will X amount of time, where both after treatment where there's a certain degree of immunity, but not forever. Okay, and there's other agents that are in there as well. They have anti-protozoal activities. They don't work. That's there. I don't do the worms. Be happy. Okay. So worms are hard to deal with. Most of the agents are pretty hard. There was a whole lot of buzz against them because, again, it was working. It seemed to be working at least on the inflammatory aspect of COVID. It was called ivermectin. And statistically, it did work. People were getting yelled at because it's the ingredient of something called horse paste. Of course, horses, get worms. The dose is like 5 to 10 times greater for the horse. Horses are pretty darn big. But for tiny doses of ivermectin, it was very effective at treating COVID and even preventing COVID. I don't want to go there. It's just, I can remember my rheumatologist, we sat there and had this discussion right during COVID, sitting there with the stupid masks on. And I'm like, I said, we've been reading a lot about ivermectin. He looked at me and said, I've been reading the studies too. He goes, ivermectin works. Why weren't we using it? That's a very interesting question. Okay. And so I'm not going to go into any of those. I don't treat them. As you can see, it can be used in people, but it had to be aware of the dose. And I'm going to stop here because antivirals go in a different category. I'll finish up this PowerPoint. And I'll go to the Nestor one and look a little bit in depth at really important antibiotics. Thanks. Goodbye. Farewell. Wiedersehen.